Hi there and welcome back to Tripplikit and part 6 of the synthesizer tutorials. And today, as promised, we will be looking at envelope generators, but before that we're going to take a look at parameters. And what are parameters, you ask? Well, let me explain. Let's take, for example, the oscillator we developed in the last video. It has three inputs: pitch, waveform, the amplitude of the second sawtooth wave, and width, the phase difference between the first and second sawtooth waves. We want to control these in real time, so for instance the oscillator pitch is affected by the note played, including pitch bend and portamento. The mean green also has a pitch control for setting octave and semitone, and a detune control for making fine adjustments to oscillator pitch. But we also want to modulate the pitch input to the oscillator, both coarse and fine, for instance with envelopes and LFOs. So each input to the oscillator, or any other sound generation or shaping module, for instance the filter, I've called a parameter, just my name. So this is the pitch parameter, and the waveform parameter, and the width parameter. A major design parameter for the mean green is to reduce noise to a minimum, specifically digital noise. To this end, we are going to specify that the output from parameters should contain no audio frequency content, or a negligible amount. This is because allowing, say, LFOs to produce audio frequencies would mean that they would effectively become oscillators, subject to all the constraints we apply to designing our oscillator. So what might cause audio frequency noise to appear on the output of a parameter? Well, we've already mentioned the LFO. Here, for instance, is a 10 Hz square wave. Now, if we look at the spectrum, we can see that there are harmonics generated all the way up the audio spectrum. We would definitely want to filter these out. Another source of noise is called zipper noise. Okay, so the reason we put lots of nice control knobs on the front of the mean green is so we can use them to control the sound in real time. And we're going to want to be able to record these changes into some kind of sequencer, which means MIDI. MIDI allows our knobs 128 values, and abruptly changing a parameter by 128th of its range could cause an audible click. Turning our knob quickly over a large part of its range gives a series of these clicks, which often makes a zip-like noise. This phenomenon is known as zipper noise. If we move the knob from end to end, in 1 second this zipper noise will be at 128 Hz. So here's some zipper noise. When looking at zipper noise, we're just going to look at the output of the parameter, not what happens to whatever the parameter controls. This simplifies the measurements, and if there's nothing nasty coming out of the parameter, we can be pretty sure it won't generate any bad effects in whatever it's controlling. So we need some kind of filter. Let's have a look at what type of filter we're going to use. Ideally we want a filter that lets everything through up to, say, 10 Hz and blocks everything above 20 Hz. Now, you can't design a perfect filter like the one in the diagram, and unfortunately anything approaching this will take a lot of processing power. Since we need a few of these filters, we'll need to use a simple filter, and unfortunately this will have a response more like this. So what type of filter are we going to use? Well, the simplest type of digital filter is a running average or smoothing filter. This is the equation for a smoothing filter. Here we take a scaling factor, say 10%, and multiply the input by it. Then we take our last filter value and multiply this by 1 minus the scaling factor. We then add these two values together. The cutoff frequency of this filter depends on the scaling factor, and its frequency response is shown in the waveform plot. This is the output when the input is a sine wave where the frequency has been swept logarithmically between 1 Hz and 1000 Hz. As you can see, the frequency response is not brilliant in the frequency range we're interested in. And this is the code to implement that filter. Note that instead of multiplying the input by a small scaling number, we shift it right, in this case by 10. This makes the code quicker. And this gives a scaling of approximately 1/1000th. Note also that to maintain the resolution, the stored filter value is 1000 times the output value. This means that we need to be careful not to exceed the maximum size of a 32-bit number, and to avoid this we may need to scale up and down input and output values. It just adds another complication. I am at some point going to do some additional tutorials on digital audio topics which aren't actually directly used in the mean green. One of these tutorials will be on filters, and here I will go into the smoothing filter in more detail, so hence the brief description here. Another type of filter is the resonant filter of the same type we're going to use for the mean green's main audio filter. We'll be looking at this in the next tutorial, so I do not propose to go into it in any detail here. However, as you see from the equations, this uses a bit more processing power, especially when implemented in integer arithmetic. However, it does look as though it performs considerably better than the simple smoothing filter, as we can see by looking at the direct comparison with the smoothing filter here. Okay, so let's try each of these filters on our 10 Hz square wave, as this is the toughest test for our filters. Remember that ideally there should not be any audio frequencies coming through the filter. And here it is through our smoothing filter. We can see it's not letting the 10 Hz through fully, and those points at the top and the bottom of the waveform will be audible. Yes, we can definitely hear the clicking. So what of our resonant filter? Here it is, and the output waveform looks pretty close to a 10 Hz sine wave, which is what we want, as all the harmonics of the square wave are at audio frequencies. And if we play it, there, you can just hear a faint rumbling, so I think that this filter will be good enough. So which one to use? Well, I think we will implement them both and select which to use on a case-by-case basis. For instance, here's our zipper noise. If we put this through the smoother type, we can see it looks fine, and if we play it, can't hear any noise in there, so it sounds fine. Right, so we've sorted our smoothing. Shall we now move on to how the parameter structure itself is going to operate? Any input to a sound generation or shaping module for instance the main filter, I have called a parameter. So the filter cutoff frequency is a parameter, and the filter resonance is also a parameter. So what does a parameter look like? Well, firstly, it has one or more inputs. An input might be a simple control lob, like the filter cutoff frequency pot, or it might be a modulation, like the filter cutoff envelope modulation. In the mean green, the filter cutoff frequency has an optional second modulation, for instance from an LFO. This means that the filter cutoff frequency parameter has 3 inputs. In fact, there is no limit to the number of inputs a parameter can have. We will look at what the inputs do in a minute. The signals coming from each input are simply summed together and then they are passed to the smoother. The smoother is selectable between the 2 types of smoothing we developed earlier in this tutorial, and also we can have no smoothing at all. The smooth value is then checked for range. Say we turn the filter cutoff frequency pot up to maximum and the envelope modulation up to maximum. This will give us a filter cutoff value of twice the maximum input allowed by the filter. To prevent this, we set a maximum value and a minimum value for the parameter, and the output from the smoother will be clipped to these if required. However, for this to work, we must make sure the value here does not exceed what can be stored in a 32-bit number. Finally, we call a convert function. This again is selectable. It might do nothing. It might simply scale the value up. It might look up the output value from a table, or it might do something specific to the parameter. So, on to input. An input takes some kind of control input and an optional modulation source. It then combines these and outputs the result to the parameter. The combine function is also selectable, so it can do a simple multiplication and scaling, or something specific to the input. If there is no modulation on this input, the combine function will probably still be required, even though it's not actually doing any combining. Right, I think I'm going to leave it there for parameters for now. As we continue to develop the mean green, I will explain their implementation in more detail. For now, let's have a look at envelopes. Initially in the mean green, we're going to implement the standard ADSR type envelope that you see on the screen and that you find in most synthesizers. We may well come back and see if we could add any enhancements to it in a later tutorial. Okay, so when we get a note on, the attack phase starts. We're going to use a linear attack as this is easy to implement and I find it works absolutely fine. When the attack reaches the maximum value, we enter the decay phase. Here the envelope decays exponentially towards the sustain level. There is no actual defined sustain phase, however the envelope will have decayed to near enough the sustain level after a certain time. This time depends on the decay rate and is what we take to be the decay time. When a note off is received, the envelope enters the release phase where it exponentially decays towards 0. At some point the envelope will have decayed to near enough 0. The time to do this depends on the release rate and is what we take to be the release time. Okay, so now let's look at how we implement an ADSR envelope. Okay, so here's the envelope do function, which is called every sample for each envelope to update that envelope. 4 parameters control the envelope: the attack increment, the decay rate, the sustain level and the release rate. Now let's say we've had a note on message. This will cause the envelope to go into the attack phase. In the attack phase, every sample we simply add the increment value to the envelope output value. If the output value is now less than the increment value, we know that it has gone over the maximum, so we have reached the end of the attack phase. The calculation on the screen shows this happening for an 8-bit number. In this case, we set the envelope output to the maximum value and move on to the decay phase. Okay, the decay. The decay phase is an exponential decay down to the sustain level. This, in fact, works the same way as the smoothing filter we discussed earlier in this tutorial. The basic equation for this is shown on the screen. Now, if we were doing this in floating point arithmetic, this is pretty much what the code would look like. However, in integer arithmetic, we have to watch out for our calculations being too big to fit in a 32 number, or so small that we lose resolution. Okay, now first we get the difference between the current envelope output and the sustain level, which is the level we want the decay phase to end at. Now we multiply this by the decay rate value. The decay rate value actually needs to be scaled up so that this calculation maintains plenty of resolution. As a result, we then have to shift the result down to get the actual value we want to subtract from the envelope output. Note the decay parameter uses a second output from the parameter. This is available for situations like this. Finally, when we receive the note off message, we go to the release phase. This works in exactly the same way as the decay phase, but here we are decaying down to 0 rather than the sustain level. Okay, so let's have a look at our envelope in action. Okay, that's done. Here I've generated 4 notes with the same envelope settings, but I've ramped the oscillator wave and width parameters during each note. I'll quickly show you the little sequencing language I've developed to do this. Okay, you can set the tempo here, and then you can set parameter input values, ramp parameter input values over time, and include note on and note off messages, and then you can run to a certain time. This is not really part of these tutorials. I only developed it for test purposes, so I'm not going to go into it in any detail. Okay, so here's the result. You can see the audio output is in the left channel, and the right channel I've just included the envelope output so I can see what it's doing for test purposes. And as I say, I've ramped the oscillator parameters, so this accounts for the change of tone as the notes play. So this sounds like this. Okay, so now let's have a quick look at how the oscillator controls work. The mean green is a hardware synthesizer, and as such it has physical controls. To justify designing, building and using a hardware synthesizer, over a soft synth that is, it has to be tactile, physical. The controls are meant to be used in real time. This means that all the controls have to feel good and work intuitively. We don't want any controls that, for instance, seem oversensitive at one end and don't seem to have much effect at the other. So, as a starting point, the attack and decay times are going to vary logarithmically with the control knob position. That is, the change in pot position between 100 milliseconds and 200 milliseconds is the same as the change in pot position between 1 second and 2 seconds. The attack and decay time pots will range between 10 milliseconds and 10 seconds. So here's how the attack changes over the control range. For each note here, the control has been increased an equal amount between its minimum and maximum. So, here's how the decay changes over the control range. Again, for each note, the control has been increased an equal amount between its minimum and maximum. You get the idea. So here's how the sustain changes over the control range. The sustain level is linear with the sustain control. Again, for each note, the control has been increased an equal amount between minimum and maximum. And finally, here's how the release changes over the control range. Again, for each note, the control has been increased an equal amount between its minimum and maximum. The release code is the same as the decay code, so I think we'll take it that it works alright. I'll spare you having to listen to the whole of this one as well. Okay, so those all seem fine for now, but we may end up tweaking them when we actually start using the mean green in anger. Also, in a later tutorial we will come back and look again at the issue of percussive sounds with very fast attacks. Finally, a last word on parameters. None of the envelope controls, attack, decay, sustain or release, are modulatable by any other envelope or LFO. I just don't think this is a very meaningful thing to want to do. The attack, decay and release parameter outputs are not smooth and are looked up directly from tables. This is because they're controlling rates, not levels, so they shouldn't introduce zipper noise when they're changed. Now the sustain value is currently multiplied up directly from the pot value and hence would be a prime candidate for zipper noise. However, it is only active during the decay phase, and the decay code itself acts as a smoother, even on the shortest decay time. And finally, a word on the joys of software development, and how unexpected things can come back and bite you. While checking for zipper noise on the sustain control, I discovered that if I turned the sustain control up, all sorts of strange things started happening. This was because I was using unsigned arithmetic in this calculation. Turning the sustain control up meant the sustain level was higher than the output, so the calculation produced a very large positive number instead of a very small negative number. So to overcome this, I then changed the envelope over to using signed numbers. I then found that this method of extracting the most significant word from the multiplication didn't work properly. So as you can see, I went over to shifting by 16 bits instead, and now it all works fine. Okay, now we have envelopes and parameters working, so I guess that's about it for this tutorial video. As ever, the code and the examples can be downloaded if you want to look at them or even use some of the code. And there are links listed in the video description. And again, as usual, if you have any questions about what I've covered in this video, don't hesitate to get in touch via the video comments or via email. Again, the email address is in the video description. So next time we're going to be looking at two things. Firstly, the oscillator mixer, which will also incorporate the main envelope and the key velocity sensitivity code, and also we're going to be looking at the main audio filter. And once we've got that in place, we've pretty much got a basic working synthesizer. So until then, it's goodbye from Tripplikit. Goodbye.